Okay, welcome to our review of Unit 4 integrals before the AP exam. You can find all the formulas that you'll use over here on the right, but you should have them already. Printed formula sheet somewhere in your notebook. Keep that handy and study it. It'll make our problems go a lot faster. I will be doing the odds. As before, you'll do the evens for homework, and the homework problems are timed to be less than 30 minutes. To help you keep track of your time, I've put little indicators next to the even problems to make sure that you are finding the right pace. So let's get started. For number one, I'm going to use the power rule, which simply says to take the exponent, add 1 to it, and then divide by your new upgraded exponent. So that's what we're going to do with the first term and all those that follow. This will become 2x to the power of 4 over 4. I'm copying down the constant minus 4. And now notice we have a fraction here. So for fractions, I always like to write the plus 1 and leave a space after the constant. So that'll be 3/4 plus 4/4, which is x to the 7/4. And now you see why I left the space here, because I'm going to times by 4 over 7, or divide by the new exponent. Next term, I'll copy down the constant, that's 7/3. But notice that it leaves me with 1 over x squared. Now, I can't use the power rule if the exponent's in the denominator. So I can either rewrite this as x to the -2, then add the 1 and divide, or I can leave it there but recognize that that is one of my formulas. The integral of 1 over x squared is -1 over x. And the integral of 1 over radical x is 2 root x. The next term is a constant. So it looks a little tricky because it has an e here, but that's not e to the x. So we will not use this rule. Simply a constant, what do you do with any constant? Copy it down, and then we add an x to it, plus c. So the AP exam will accept this as a correct answer in FRQs. There's no need to simplify further unless you want to. I'll just do that for fun. Again, the AP exam graders will accept anything that's equivalent to your final answer, the final correct answer. So they'll accept both. In my opinion, no need to simplify. Save yourself the trouble and the potential simplification errors. You're good to go. Okay, for number 3, we can't apply the power rule unless we take care of this multiplication first. So let's distribute. And in order to multiply s and square root s, I need to make my exponents visible. This will become s to the 1/2. So now when I distribute, 4 times 3 gives me 12. S to the 1 times s to the 1/2, we add the exponents, gives me s to the 3/2, minus 8, and then s times s is s squared. So we haven't actually integrated yet. Now we can use the power rule. So that becomes s to the power of 5/2 times 2 over 5, minus 8, s to the 3 over 3 plus c. All right, number 5 also requires us to do some simplification before we can use the power rule. So let's break this up. Into 3 different terms. Okay, now we're going to simplify each of these terms. So I see here I need n squared divided by root n, meaning I'll subtract the exponents. So let's make our life easier and rewrite these as 1/2. I'm going to leave this one untouched because that's a formula that I can use, but for these I'll have to do some math. So the first term becomes, let's copy down the 3/2. 2 minus 1/2 leaves me with n to the 3/2. Constant comes out first. 1 minus 1/2 leaves me with n to the 1/2. And I rewrote that so I can clearly see my constant and my variable term, dn, at the end. So let's use the power rule. For the first problem, we're copying down a 3/2, leaving a space. That's n to the power of 3/2 plus 2/2 is 5/2 times 2 over 5, plus 7/2, leave a space. That'll be n to the power of 3/2 times 2 over 3, minus 1/2. And The integral of 1 over radical n is just 2 root n plus c. That's a formula. You can leave your answer like this. If you wanted to simplify, we can do that. Just be careful not to make any errors. Number 7. Okay, so I have 3 cosine of some expression. It's actually a linear expression. Can you see I have a slope of 1/4? So whenever we have a linear expression, we want to divide by the slope of that linear expression. This accounts for the chain rule when we take derivatives. Instead of multiplying by the slope of the inside, we divide by the slope of the inside. So the integral of 3 cosine would be 3 sine. Our monkey stays the same, but we'll divide by the slope. Well, the slope here is 1/4. So dividing by 1/4 means we'll multiply by 4. Let's do the same thing on the next term. I have negative 2. The integral of e to the monkey is just e to the monkey, but we have to divide by the slope. Here my slope is negative 1, so we'll divide by negative 1. Next, plus 5. The integral of secant squared is tangent. The monkey stays the same, 6t plus 3, but we'll divide by the slope. And for our last term, we can take out the 3/2 as our constant, and we're left with 1 over x, the integral of which is natural log absolute value of x, plus c. You can leave your answer like this, and that's perfectly fine. Or you can take the extra step and simplify, which is not necessary, but just for practice, I did it here for you. So number 9. So now we're starting to get a little more complicated, but remember to divide by the slope if it occurs. And then the other thing is, if you're stuck, just always copy down the constant in front first. So this is 3/4. And now I need to think what to make of this 1 over radical x minus 1. It looks kind of like the sine inverse formula, but notice that sine inverse has an x squared. And it's 1 minus x squared, not x minus 1. So this is not a sine inverse. Instead, we'll have to view this as 1 over root monkey. And the integral of 1 over root monkey is 2 root monkey divided by the slope. So I'm seeing this as 1 over root monkey, which becomes 2 root monkey divided by the slope of that inside guy. Now the slope of that is just 1, so it didn't do anything for us. But if there was a 2 here, then I would have divided by 2, because that's the slope of the inside expression. So in the second term, let's do the same thing. This is the inside expression, okay? So what should we copy down? 4 over 5, and we should view this as 1 over monkey squared. The integral of 1 over monkey squared, if you recall, is negative 1 over monkey. So we're going to multiply by negative 1 over monkey, which is 3 minus x. What's the slope here? It's also negative 1. So what I'll do is I'll just make this a positive. Okay, for the next term, write down the constant in front. What could we copy down? So that 2 can't come out with the 7 because it's part of this. So we can just copy down the minus 7 and then view this as 1 over monkey. What's the integral of 1 over monkey? Do you remember? It's the natural log of the absolute value of monkey. What do we need to remember in the last step? To divide by the slope, like that. Great. And now the last term is plus 8. And the integral of 1 over 1 plus x squared is really tan inverse of x. And we're done. You can leave it like that or simplify in the last step. Moving on to number 11. So now we're starting to get into FTC2. And here's how you know when to use FTC2. Look at 11. It says find the slope of the tangent line to this integral expression. Well, slope of the tangent line just means we're finding the derivative. Anytime that you're asked to find the derivative of an integral, well, this is the derivative. This is the antiderivative. They will undo each other. So I repeat, there's no need to take the integral. You don't need to use the power rule here. because the derivative undid that integration for you. So all you're left with then is the plugging in process, top minus bottom. So when you take the derivative of the integral, you're going to cancel them out and then start plugging in g of x anywhere you see x in your expression. So it'll be like this, h of whatever that top expression is. But we have to account for the chain rule, so times g prime minus, and now let's plug in the bottom, it'll be h of f of x, and don't forget the chain rule, times f prime of x, just like that. Okay, that's what FTC2 is all about. It's when you're taking the derivative of the integral and they cancel each other. Now, if the bottom, let's say, instead of f of x, it was some constant c. Well, then what I would have done was plugged in c here, h of c times the derivative of a constant is 0. So because I'm taking the derivative of a constant, it will cancel out this entire expression, so I'm just going to minus 0 anytime I have a constant. Now, if the constant had been up top and the function had been at the bottom, then I would have started my answer as 0 minus and then the plugging in. Cool. So coming back to our problem, find the slope of the tangent line to this integral. So what are we going to do? We're going to show the slope of the tangent line by writing the derivative. Notice that the derivative and the integral cancel, and then we'll use FTC2 here. So let's plug in the top function everywhere we see a variable. So we're going to write x cubed squared minus 2 times x cubed. And this entire expression will be multiplied by, don't forget the chain rule, by 3x squared, which is the derivative of the upper limit. Okay, now we do minus the same with the bottom. Or we could remember that when we're dealing with a constant, it just becomes 0. So our final answer here is, we got the 3x squared out in front, and we'll distribute it for a final answer of 3x to the 8 minus 6x to the 5th is our answer. Let's apply the same thing for the next problem. So for these problems, which by the way are very frequent on the FRQ portion of the AP exam, here's how you should approach it every single time when you're finding a value at a number. First, write down what you need to find first. If I need f of pi, I should first find f of x. Well, I'm already given f of x. So my next step, I immediately just plug it in. F of pi will be the integral from 0 to pi of 2t plus 3 sine t dt. And we know how to do the right side. We know how to evaluate this. It's just saying find the integral, plug in pi, plug in 0. So to find the integral, we'll use the power rule. Evaluated from 0 to pi. So the 2's will cancel, leaving me with pi squared minus 3 cosine of pi minus parentheses 0 minus 3 cosine of 0. Okay, finishing that up. So my final answer is f of pi equals pi squared plus 6. Okay, and the key to getting that answer there was just plugging it in because we already had f of x. So we took the integral and then plugged in. There's nothing fancy going on here. Let's go to the second part. Part B says find f prime of pi. So first we should find f prime of x. Well, if you look at what we're given, to go from big F of x to big F prime of x, we have to take the derivative on the left, meaning that we'll need to take the derivative on the right also. So let's write that. The derivative of 0 to x, the derivative of that integral. These problems freak students out, but they're really some of the easiest problems you can get on the exam. Again, anytime you're taking the derivative of an integral, you're canceling. The operations are undoing each other. So remember last time how we did 2t squared over 2? How we actually had to find the integral? Well, this time we don't need to because the integral was already canceled. So we just plug in the top and then plug in the bottom. So we're going to get 2x plus 3 sine x, all of that chain rule times 1, the derivative of x, minus, and the bottom is a constant, so we're just going to write 0. So f prime of x is really 2x plus 3 sine x. Well, now I want to plug in pi. So f prime of pi will be 2 pi plus 3 sine pi. Now I know sine of pi, sine is the y value, so it'll just be 0. So that means that f prime of pi is just 2 pi. Let's do the last problem. Part C, f double prime of pi. So what should we find first? First, find f double prime of x. So from part B, from this step, I know that f prime of x is 2x plus 3 sine x. The second derivative becomes 2 plus 3 cosine x. Well, now we'll plug in pi. I know that cosine of pi is -1, which is -1, and that's f double prime of pi. Really easy problems here when you get to use FTC2. Number 15 is a lovely problem that's frequently asked on the FRQ portion of the AP exam. So they'll give you a graph defined as f of x, and then give you a function g, which is defined as what we call the accumulation. We call this the accumulation function. So it's the integral from 2 to x of f of t. So basically, it's the area under the f curve from 2 to some number. So let's say that number was 4. It'd be the area under the curve from 2 to 4. Or we could say the area, let's say it was instead from 2 to 0. Then it would be this area from 2 backwards to 0. Anyway, that's why we call this the accumulation function, because it's the accumulated area under the curve up until any value of x. The first thing I want you to do is take the derivative on both sides. So immediately we'll define what g prime of x is. Then we have to take the derivative on the right, so I'll indicate that with my d dx, and then everything else I'll keep as is. Now recall what we're really dealing with here then when we take the derivative of an integral by FTC2. We'll just cancel these, they undo each other, leaving us with f of, I'm plugging in the upper limit, times its derivative, minus, I'm plugging in the lower limit, but it's a constant, so that collapses to 0. So really what we have is g prime of x equals f of x by FTC2. And from there, we can also say, well then g double prime of x, that's just the derivative one more time. And these two functions are going to be crucial in setting up the rest of our problems. So let's look at A. It says find the x values of the relative minima and maxima of g. So the relative maximum of g occurs where g prime switches from positive to negative. And then a minima will occur where its slopes switch from negative to positive. And that's how we would normally go about these problems. But this graph isn't g. This graph has nothing to do with g, it's defined as f. So rather than speaking of g prime is really just f of x. And so we're interested where f switches from positive to negative. F switches from positive to negative right here at x equals -2. To the left it's positive, and to the right it is negative. So we will say relative max at x equals -2. Since now I'm looking for a relative min, so I need where g prime of x, which is f of x, to switch from negative to positive. Well, let's see. I was going to say at 2, but it actually doesn't work out because on the left it's negative, f is negative, and on the right f is negative, so it never makes that switch over to the other side. Hence, there is no relative min. Part B, identify where g is increasing and decreasing. So let's start with increasing. Normally, g is increasing where g prime of x, which is f of x, so where g prime is greater than 0, and that would be where we're increasing. And then decreasing would occur where g prime of x, which we're defining as f of x, I'm getting that again from right here, is less than 0. So what does this mean? Again, we're not interested in the g prime part because we have the f graph, so let's focus on that. We want to know where f is greater than 0. That basically just means where we're above the axis. That's true from here to here on the interval from -3 to -2. since g prime, which is f, is greater than 0. So g is decreasing where g prime, which is f of x, is less than 0. So we're interested in seeing where our f graph is below the axis, where it is negative. From here to here to here, it's not true at x equals 2 because at that point it equals 0, and we're interested in where it's less than 0. Negative 2 to 2, and then again from 2 to 4, since it's decreasing since the slopes of g, which is f of x, is less than 0, are negative. All right, part C. Identify where g is concave up. G would be concave up where g double prime is greater than 0, but g double prime is really f prime, where g double prime, which is f prime, is greater than 0. Okay, that'll be concave up. And then concave down where g double prime, which is f prime, is less than 0. So we're going to be concave up where f prime is greater than 0, means that the slopes of f are positive. That means that f is increasing. F prime greater than 0 means the slopes are positive, meaning f is increasing. So where are our slopes positive? Well, our slopes are positive all along this region. Check it out. It's a positive slope, right? So f is increasing from 0 to 2. So we're concave up on 0 to 2 since g double prime is greater than 0, which means that f prime is greater than 0. And then we'll be concave down where the second derivative of g, which is the first derivative of f, is less than 0. So if f dash is less than 0, that means that the slopes are negative. If the slopes are negative, that means that the original function, f, is decreasing. So where is that true? Well, f is decreasing here to here, as well as there to there. So our answer is negative 3 to 0, and then 2 to 4. Since g double prime of x, which is f prime of x, is less than 0. Okay, part D. Identify where g of x is increasing, so that means g prime of x, which is f of x, is greater than 0, is positive, and where g is concave down. So g is concave down where its second derivative, which is f prime, is less than 0, concave down. So again, we're only focusing on these two parts. So what does it mean for f to be greater than 0? Well, that means it's above the axis. And what's it mean for f prime to be less than 0? Well, that means the slopes are negative, meaning that f is decreasing. So we need to look where f is above the axis and decreasing. F is only above the axis from here to here. And it also is decreasing. So that's our answer, from negative 3 to 2. Part E, identify the x value of the inflection points of g of x. So we know that inflection points occur where the second derivative switches signs. That means that g went from concave up to concave down, or concave down to concave up. So we need to have a sign switch. So again, we don't deal with g double prime. G double prime is actually f prime of x, and that's what we need to switch signs. Well, if f prime is switching signs, that means that f prime can switch from positive to negative, or f prime can switch from negative to positive. Let's think about what that means. If f prime is the slope switches from positive to negative, that means that my graph of f switches from increasing to decreasing. So basically we're looking for a max. Or if f prime switches from negative to positive, that means that the slopes are switching from being negative slopes to positive slopes. So we're looking also for where it's switching from decreasing to increasing, aka a relative min. So That's what we're looking for. Let's see where f prime switches signs. Okay, on this region, f prime of x is negative. It's also f is also decreasing from here to here, meaning that the slopes are negative here as well. In this region, though, f prime is positive, since the slopes are positive and the graph is increasing. So the question was, where does f prime switch signs? Our answers are at x equals 0 and at x equals 2. Since g double prime of x, which is f prime of x, switches signs. Let's move on to number 17, which is the same function, just different style of questions. So I've gone ahead and already found the areas of each of these pieces. I started by dropping the perpendiculars from the endpoints and all sharp corners. And I actually found this piece here by taking the area of the full rectangle and then subtracting the area of this circle for whom the radius was equal to 2. So that's the process that I went through. The question says to find the absolute max and min of G. So for these questions, absolute extrema, we need to consider endpoints, which are x equals negative 3 and x equals 4. We'll also need to consider critical points. Since we want the absolute max of G, we need the critical points of G, which occur where G prime equals 0, which is f of x, where that is equal to 0. And f equals 0 over here at negative 2 and at positive 2. Those are our x-intercepts. So we'll consider negative 2 and positive 2 also. Our next step is to evaluate the function g at all those points. So we're going to plug in 4 of them. So we have g of negative 3, g of 4, g of negative 2, and then g of 2. So first let's find our g of x function. There it is. And we're not taking the derivative or anything. We're just plugging in negative 3 into x. Well, we know how to do that. That just means that anywhere on the right side of the equation that says x will also plug in our value. So we're only plugging in negative 3 into all the x positions, not where it says t. Okay, don't plug it in there. The integral from, where was it? From 2 to x. In this case, 2 to negative 3 of our f function. Well, this just means find the area under the curve of f from 2 to negative 3. So we want this area. And we're going backwards. So let's begin with the first piece next to the semicircle. It's going to be 4 minus pi. And since I'm going backwards, that's going to be a positive 4 minus pi. I'll add the 2 and then subtract 1/2. Simplifying, 4 plus 2 is 6 minus 1/2, that's 5.5, which is 11 over 2 minus pi. Great, let's do g of 4. So g of 4 is the integral from, same deal, we're plugging in 4 where we see x. This time we want the area under the curve from 2 to 4. 2 to 4. Okay, easy enough. That's just going to be 4 minus pi. But careful, since we're going forwards this time, since that area is below the axis, we need to change it negative. So I'll distribute in the next step. That's negative 4 plus pi. Okay. Next, g of negative 2. Let's plug in negative 2 into the top, where the x was. So from 2 until negative 2, that's this whole region here. Since we're moving backwards this time, from 2 to negative 2, we're going to have 4 minus pi, and we will also add the 2 on, leaving us with 6 minus pi. Last but not least, let's do g of 2. So that's the area from 2 to 2 of f of t dt, and we know that if we start and end at the same spot, there is no area at all. The answer there is just 0. Now our job is to figure out which of these is the highest and lowest values. So let's use some smart approximation methods to compare. Well, 11 over 2, that's like 5.5 minus 3.1, which leaves us with approximately 2.4, okay? Approximately. And we're done. Okay, let's move on to part B. So let's break this part B up into 3 parts itself. First, we'll find g of negative 1, and then we'll find g prime of negative 1, and end with g double prime of negative 1. So the first thing is g of negative 1 is just plugging in our value from 2 to negative 1 of f of t dt, plugging it in exactly as it says. And we're going to go from 2 to negative 1, the area under the curve. So I know the area from 2 to 0 is going to be 4 minus pi. But then the remaining area from 0 to negative 1, well, that's a trapezoid. To find the area of a trapezoid, I'll take the average of the bases, so base 1 plus base 2, and I'll take their average times the height. When I say the bases, I mean these parallel pieces. Okay, so the first base on the left, the height is 1. The second base on the right, the height is 2. Taking their average, we divide by 2, times the height, or the distance that's across, and that would just be 1. So 1 plus 2, that's 3/2. Okay, so that's going to be plus 3/2 since we're moving backwards, so areas below will be positive. Next, g prime of negative 1. So g prime of x is really just f of x. Therefore, we're interested in f of negative 1, meaning we'll find the value. If we're given the graph of f, we just need to find the y value when x is negative 1. Well, when x is negative 1, we're here. The y value is also negative 1. And last one, g double prime of negative 1. Well, we know g double prime, based on our box, is just f prime. So we're interested in f prime of negative 1, which means we're interested in the slope of f, of graph f, at x equals negative 1. So let's go there and count some rise and run. Well, at x equals negative 1, here's the slope. We can count based on these points around it, and so we can find the slope at this point. We're going down 2, over 2, so our slope is also negative 1. And those are our answers. So see how we did these 3 things differently? The first one, g of negative 1, we just plug it into the top. It becomes our upper limit. And then when we're finding this value, we're looking at the area under the curve, because that's what the integral is. For the second one, since we're finding f of negative 1, that's just the value. And then for the third one, for f prime, we're interested in the slope. So we went area, value, slope. Okay, let's do C. Find the average rate of change. Okay, these are like magic words. Whenever you see average rate of change, you should be thinking m sec. So the average rate of change of g over this interval will be g of 4 minus g of 0 all over 4 minus 0. Let's do a sidebar and find what g of 4 is. So we know that g of x is defined as the integral from 2 to x. Therefore, g of 4 will be the integral from 2 to 4 of f. The integral from 2 to 4 of f of t dt. So we're interested in the area under the curve from 2 till 4. From 2 to 4, that's this region right here. The area under the curve is 4 minus pi. But careful, since we're going forwards and that region was below the axis, we're going to flip it negative. So actually, The answer there is -4 plus pi. Okay, let's do g of 0 next, which is integral from 2 to 0 of f of t dt. The area from 2 to 0, we're going backwards this time, is going to be 4 minus pi, but positive. So now we can plug in and finish our work. So g of 4 was -4 plus pi minus parentheses 4 minus pi all over 4 for a final answer of -2 plus pi over 2. That is the average rate of change of g over that interval.
Now this next problem asks us to find the equation of a tangent line to f at x equals 9. So always we know we're going to find a point being 9 comma something. That's our x. We'll find the y. And our slope. Meaning we'll find the slope at x equals 9. So we want f prime of 9. Well, the slope is easy enough because they gave me f prime right here. So all I have to do is plug in 9. So f prime of 9 is going to be 2 root 9 minus 3, which is 6 minus 3, which is 3. So that's going to be my slope. But now for the point. Well, normally I could just plug in 9 into my f function, but I don't have f. I only have its derivative. So since I have f of a and I have f prime of x, we're going to use the net change corollary, or the net change theorem, which says to find the endpoint on an original function, take a starting point and add to it the change. And the change is defined as nothing more than just the integral of the rate. That is net change from a to b. So it's always important that your ending point is your upper limit. So let's find f of 9 in that way. F of 9 equals f of 1 plus the change in f from 1 to 9. Recognize that since this is f, inside the integral must be f prime. Okay, so now we can plug in. F of 1 is just -3. Integral from 1 to 9 of this function, 2 root x minus 3. So now it's a straightforward integration problem. We just need to remember to add that 3 at the end. Okay, so the integral of 2 root x is going to be 2 space x to the 3 halves times 2 over 3 minus 3x, integrating from 1 to 9, and we'll add 3 at the end. So this becomes 4/3. So we really have 4/3 times 9 to the 3 halves minus 3 times 9 minus parentheses 4/3 times 1 minus 3 times 1. And we finally get our point. F of 9 equals 23 over 3. Okay. So now it's as simple as just plugging it into y minus y1 equals m, which is 3, x minus 9, and we're done. So we used our point from here, I'll highlight red, and we used our slope from here. Okay, for this final example, it says if f is increasing, will a right Riemann sum be an under or over estimate of the actual area under the curve? So to answer this question, simply make a quick sketch. Let's start with sketch number 1 on the left side. So you can make a right Riemann sum by starting at the right edge of your graph, dropping the perpendicular down to the x-axis, and then extending your rectangle leftward. And we'll repeat that process until we either fill in the entire area, or let's, for demonstration purposes, just say we have n equals 3 rectangles. So you can see that the actual area under the curve is this. But our estimated area under the curve is much more. We've overestimated. And so that will be true anytime we're increasing. So our right Riemann sum will always overestimate our increasing functions. Now, in this example, we had a straight line, so there was no concavity. But I want to show you that it's also true regardless of whether we're concave up in situation 2 or concave down. But don't take my word for it. You can pause the video and try it yourself. So again, we have visual evidence that we're overestimating the actual red area under the curve. In both cases, we have all this extra space on top. And so again, for these problems, just simply draw a sketch, but it's important to know as a shortcut for the AP exam that Riemann sums over or underestimate based on if the function is increasing or decreasing, not based on concavity, as we could clearly see. It only mattered that the graph was increasing.